Okay, so today I wanted to talk a bit about sort of external motivation for various elaborate constructions we're trying to discuss here. And I will do it along the lines of introduction to Schreiber's book, Differential Cohomology in Cohesive Infinity Topology. And the main motivation for this business about cohesive topology and about differential cohomology in this setting comes from physics. So that's the notion of pre-quantum geometry. So let me first of all make a disclaimer that in no way, shape, or form I am an expert in physics or differential cohomology for that matter. So this talk will be mainly just some vague ideas about why what we're doing is good. So since this is mainly a learning seminar, it's not like some, I don't know, expert coming here to tell you that that's an absolute truth and there's nothing else to the matter. So knowing that, let me begin by just discussing some very vague idea of how two worlds of physics are related to one another. So first of all, we have classical physics, which are taught in courses on, I don't know, classical mechanics or Hamiltonian mechanics or whatever kind of mechanics you like. And then we have quantum physics, which are obviously taught in courses on quantum physics, quantum mechanics. And what is the relationship between the two? So in one direction, we perform a certain operation, which is called quantization, which sort of allows us to obtain a more intricate structure, which describes the quantum behavior of systems. For example, mathematically, that can be something like taking a Poisson bracket on smooth functions on a manifold and deforming it into a commutator bracket in some non-commutative algebra. So something called algebraic deformations. So during quantization, one often sees that out of nowhere there appears a small letter h, which denotes a quantum parameter, which explains this sort of local structure, which is inherent to quantum physics. And this example with deformation of a Lie bracket sort of suggests how classical physics could be obtained from quantum physics. Basically, we just need to take a limit. So we drop this extra local structure and we obtain classical mechanics, for example. So that's just a very vague idea, nothing concrete and nothing precise. But let's think a bit about some problems that can arise while we do that. So first of all, when we do this quantization, we do not necessarily get a well-defined theory. So usually this quantization process only works in a small neighborhood of classical physics, so to speak. So we always assume, for example, that this deformation parameter is small. It is, in a sense, it's this idea that we can only do it in a small neighborhood is why the result of this naive quantization, if you want, is called perturbative quantum physics. So it means that it's, in a sense, it's classical physics up to a small perturbation. So we can't really get something that is very different from classical physics. And that's one reason why we need something else in this picture. So here we have just two worlds, but actually we need a certain third world where which sort of interpolates between classical and quantum physics. So this is precisely why we need pre-quantum something. In this case, it's pre-quantum geometry. So it works basically like this. We take this pre-quantum system or pre-quantum object, and when we perform some operation which is called geometric quantization, and in return we get a bona fide quantum something, theory, system, object. It depends. On the other hand, this pre-quantum something is usually obtained from classical something by adding some global coherence data. So we can then just drop this data and obtain classical stuff. But that's again very vague. Let's consider one example. So let's consider an example of Dirac charge quantization. So assume that we have some manifold, which is in our context a space-time, and assume that we have an electron on X and a field, an electromagnetic field on X. We want to study the behavior of an electron. From electrodynamics, we know that the behavior of an electron in an electromagnetic field on a manifold is governed by two form on X called Faraday tensor. And well, this is something from classical mechanics. And so we see that the behavior of a system is governed by some global invariant, global differential form. On the other hand, if we're doing things in a quantum world, we can only do things locally. So we pick a chart, a small neighborhood, and we know that on this chart there exists a one form called vector potential, such that locally its differential coincides with the restriction of the Faraday tensor. But the thing is that the Faraday tensor may not be exact. Therefore, it doesn't mean that the vector potential exists on the whole manifold. So what can be done about this? So as I said, AU may not extend globally. We may not have some form A such that D of A is equal to F. So the answer to this was given by Dirac, who made the following discovery, that actually to quantize an electron, it means to describe a connection on a principal bundle with the structure group R modulo 2p hz, where h is often referred to as Planck constant, but yeah, and it's often denoted like this. So we take R over H over so R over Z modulo H, that sort of thing. And when we take the first Chern class of this circle bundle, we obtain an appropriate quantization of the magnetic charge of this electron in this electromagnetic field. So that's the idea. So if we have some local data, we can pass to some global object, but this object will no longer have such a simple description as a differential form. We must be more intricate. So for example, here we need a connection which is a differential form valued in well, in this case, still in R, but on a different space, on the total space of a circle bundle over our space-time. So that's a bit more concrete than this previous gibberish I was talking about. Well, not gibberish, but the way I was saying was totally gibberish. But let's consider a slight generalization of this example, which occupies more modern physics research, and that is the behavior of quarks. So assume that we have, once again, a coordinate chart on space-time, and to this coordinate chart, and to a quark living on the space-time, we associate a one form, but now instead of considering it to be R-valued, we think of it as being valued in the Lie algebra of the special unitary group. And then we once again have a global form which describes the behavior of quarks in classical mechanics. But now the restriction of this global form to this coordinate chart is not just the differential of this one form, but we also have this component. So we take the wedge product of this. One moment. One moment. It doesn't make sense at all. I'm sorry. It's just something that I mindlessly wrote down, but clearly it's not how it's supposed to work.
This is the squared matrix form, yes?
Yeah.
Matrix which consists of differential forms.
Yes. It's true. It's true. I'm just confused because I was thinking that if we take a wedge product of a form of a one form with itself, we obtain zero. That's my problem here. But maybe I'm just missing something.
No, actually, you don't get zero. It is only on the maybe generators of one for, but you take the linear combinations. So yes.
Oh yeah. Right. Thank you. I was just being stupid. Yeah, and that precisely explains why when we take SU2, which is just abelian Lie algebra, we get zero here, and we get the previous example. Yeah. Thank you. That's a great point. I'm sorry for this, but as I was saying earlier, I'm not an expert in any of this, so don't get surprised. Okay, so to describe this local behavior globally means that we need to lift this form valued in Lie algebra of SUN to principal SUN bundle over the space-time, and then the second Chern class of this principal bundle will give us a number of instantons, which is just solutions of the equation of motion. So another way to describe instantons is by taking Chern-Simons forms, Chern-Simons three forms, which are just frequentizations of the wedge square of this Faraday tensor, so to speak, of the trace of the wedge square of this form. So Chern-Simons three forms are frequentizations of this of this form, of this 3 form, to a 2 gerb with 2 connection, where the notion of a gerb is just a higher generalization of the notion of a principal bundle. Okay. But the question we should ask is, what is the real generalization? I mean, certainly we can take a group of higher dimension, so SUM instead of a circle, but can we find some conceptual way to generalize this situation? So, for example, can we generalize it to p-branes, where p-branes are p-dimensional generalizations of usual particles in physics? And the way it is done, well, without a proper generalization, is the following. So if we have a p-brane, we can just, or well, if we have some high dimensional situation, we can just splice our space-time into slices multiplied by the, well, the segment which corresponds to the time variable. And then we can reduce it to one-dimensional case by taking a fiber integration. So if we have a p+1 form, we integrate it over spatial slices like this. We obtain a 1 form, and we say that this 1 form governs the behavior of our system. But this operation of slicing things up is not very good, because obviously we can have some symmetries which non-trivially intertwine time and space, meaning that this splitting does not respect these symmetries. And that's not very convenient, and it loses us a lot of information. So there should be some other, I guess, more conceptual way to generalize this, well, this approach. So another idea to
sorry,
yeah.
What are the symmetries?
Well, I mean, if we have some physical system, it can have symmetries, right?
Yeah, and
I am saying that if we split space-time into this product, which of course can be done only locally, and then we lose track of those symmetries, because we can have symmetries which do something non-trivial, not just on this factor, but it somehow mixes the 2 factors. That's just some very vague idea why it's a bad thing to do. Okay, so another way to look at this picture is by considering the following. So if we have a p+1 form, we can try to do a similar thing that was done with Dirac charge quantization, and pass from p+1 form to a p connection on a p gerb. So as I was saying, p gerbs are just generalizations to higher categories of the usual notion of principal connection with a structure group. So instead of a group, you get a higher group and stuff like that. And this manifests in the following correspondence. So globally, we have p+1 forms which live on smooth sets or manifolds. Then we perform this quantization thing, and we obtain some higher objects. They're still smooth, so they're built up from smooth parts, if you want. So, for example, Li2 group will be a 2 group where each of the parts of the Lie group, so the set of objects and the sets of morphisms are smooth manifolds, so no maps are smooth. So by passing to these P connections on P chirps, we obtain smooth homotopy types, which can be considered as generalizations of, well, higher generalizations of manifolds. And in the opposite direction, we just basically take the set of connected components and we recover the smooth set we started from. So we have this correspondence which generalizes this passage between classical mechanics and quantum mechanics, for example. And that is basically the reason why we need higher categories to really do some theoretical physics. Okay, so let's consider particular example of classical mechanics and the way we describe it, but let's try to do it in a more categorical terms. So first of all, if we have a classical field theory, it is governed by some equations of motion. Well, equations we will consider in this example equations of motion which are obtained from local variational principle. So, for example, earlier Lagrange equations for some functional stuff like that. And then such a field theory where equations of motion are obtained in this way is called Lagrange field theory. And one of the axioms of string theory says that there is not much else besides Lagrange field theories. This axiom is called holographic principle, and it states that if we have a field theory, then it is either Lagrangian or it bounds one. So it is a holographic boundary, which is just physics way of saying a boundary. Well, I mean, just physics way, but an appropriate term for this situation where we have a field theory. So it's a manifold with some abstract structure. So any field theory is either Lagrangian or it bounds one. It is a holographic boundary of a Lagrangian field theory. So kinematics of Lagrangian field theory are defined by a smooth bundle over the spacetime. And this is just the classical situation. And the configuration of a physical system or of a field theory is given by a smooth section of this bundle. So, for example, if we have, I don't know, several particles somewhere, we will consider a configuration space of these particles. It forms a bundle over a manifold, and then the configuration is given by a section of this bundle. Okay. So now let's first of all make a small explanation that sigma can be thought of as a space-time or as a world volume. So a space-time is basically a manifold where something lives, and the world volume is a trajectory of a maybe higher particle. So if we have, for example, a p-brane, which is a generalization of a zero-dimensional particle to dimension p, we can think of as volume which is spanned by a propagating brane. So brane moves around and it spans some volume, and we call this sigma. Now, if kinematics are given purely by smooth maps, dynamics are defined by partial differential equations of motion. So we want to get a conceptual understanding of partial differential equations on manifolds, partial differential equations on sections of smooth bundles over manifolds, to be more precise. So to do this, we will need a very useful construction, which is of jet bundles. So if we have a smooth bundle, a jet bundle is a bundle over the same manifold, which is defined by the following universal property. So if we have a map, a point on our manifold sigma, then each lift of this point into the jet bundle corresponds uniquely to a lift of the formal neighborhood of this point in sigma into the initial bundle E. So this is just a fancy way of saying that the jet bundle is assembled from, basically jets of all possible, all possible sections, I guess. So if we have, for example, a tangent bundle, then we will get as J0 will get the cotangent bundle, then we will get if we have a tangent bundle, then as I guess I'm meaning to say that if we have a cotangent bundle, then the zero jet will be just the cotangent bundle itself, then the product of the cotangent bundle and R, and so on. So basically, there is, of course, an explicit construction of the jet bundle using Taylor approximations of sections, but it can be conceptually explained like this. So we use this universal property to explain that, the lifts of points into jet bundle correspond to lifts of formal neighborhoods into the initial bundle. Okay, so we have the following way of taking an infinite extension of a section of a smooth bundle. So if we have a section of a smooth bundle, we obtain a section of the jet bundle which covers this section. So we have three stages. We have the word volume, we have field bundle, which corresponds to our field theory, and then we have the jet bundle of this field bundle. Basically, physically speaking, this infinite extension corresponds to the fact that we say that we know how the system behaves if we know not only the section of this field bundle, so the configuration, but also the values of all derivatives. So in a sense, this principle that we can describe the behavior of a system if we know the values of all derivatives is about that. So the system is uniquely determined by the infinite extension of its configuration section. Okay, so now let's think about the relationship between morphisms of bundles and differential operators. So if we have a bundle map from a jet bundle into another bundle over sigma, then we have a differential operator on sections of these bundles, which operates like this. So we take a section, then we map it into the composition of F and the infinite extension of phi. Okay. So now if we can associate to each bundle map a differential operator, we can define the composition of such differential, well, we can determine the composition of such differential operators using the following diagram. So we obtain what is called a Claisley composite of these differential operators. So we start with the jet bundle of E. Then we have a canonical map into the double jet bundle of E, which works like this. So we just reshuffle the derivatives. So it's a manifestation of the fact that if you take a P plus Q jet of a smooth map, let's call a smooth map like this, then we have a, well, canonical, there is a canonical way to associate to it P jet of the Q jet of the same map, which comes from the fact that basically taking derivatives is a commutative operation on infinitely smooth functions. And that means that if you take P plus Q derivatives, it is the same as taking first all Q derivatives and then taking all P derivatives of those derivatives. So we have this morphism of bundles. Then we can apply the jet bundle functor to this morphism of bundles. And then we can apply G at this stage. And we obtain a composite, which is called Claisley composite, which determines the corresponding differential operator on sections. So this reshuffle map endows this J infinity over sigma with a structure of a comonad. So we have a map from G infinity to G infinity, J infinity, and obviously we have a canonical map from J infinity to identity, which just forgets about this extra structure given by jets. So there is obviously a canonical projection from the jet bundle to the bundle itself.
Sorry, what is the definition of F and G?
Oh, F and G are just some morphisms from J infinity E to one moment, to F, and G is a morphism from J infinity F to G. So as a result, we obtain a composition which is a morphism from G infinity E to G. In a moment, I will explain how it is related to the general notion of a Claisley category for a comonad. But yeah.
What is the category in which we consider these arrows?
Oh, that's the category of bundles over sigma.
Okay.
So yeah, J infinity is a comonad in the category of bundles over sigma. So I should probably write sigma everywhere here. Okay, so what is a Claisley category in general? Well, if we have a comonad, then the objects of a Claisley category of this comonad is just the category C itself. And a morphism in the Claisley category between two objects corresponds to the following morphism F tilde, which is a morphism in category C between P of C1 to C2. And the composition works exactly like we described earlier. So we take P of C1, we apply the structure morphism of a comonad, so we have a morphism from P to PP. And then we apply P to F1 tilde, and then we apply F2 tilde to get C3. So we get what is known as Claisley composite of two morphisms in the Claisley category. So as you can see, this example we just gave earlier with the jet bundle is just an example of Kleisli category for the common-net J infinity. Okay, so that's a way to conceptualize jet bundles over manifolds. And now we can consider the Kleisli category of this common-net. And as it turns out, well, it's quite natural that this category is actually precisely the category of differential operators over sigma. It can be regarded as a definition, of course, but we can separately define the category of differential operators, where objects are differential operators on, between sections of smooth bundles of over sigma, and where morphisms are precisely well, morphisms which preserve these differential operators. So it works something like this. Okay. So as an example, we can consider the Durand differential, which is just a morphism of bundles like this, and it corresponds to what is called the horizontal Durand differential, if we consider again, I'm not quite sure that I'm saying the correct thing here, but yeah, no, I think that's correct. So the Durand differential is a morphism between the sections of this thing here, and we can consider the corresponding morphism between the corresponding morphism in the Kleisli category. So and this is just a morphism of bundles. Okay. So we obtained this category of differential operators. Then a Lagrangian for field theory is just a morphism from this field bundle to this field bundle. So this is called globally defined local Lagrangian. So the local nature is manifested by the fact that L in actuality corresponds to a morphism from J infinity of E into this bundle, because of the Kleisli construction. So we consider it as a morphism in differential operators, and it means that this is actually a morphism of these bundles. And so if we unwind the definitions here, L is a function which sends configuration, which is just a section, to plus all its derivatives to a globally defined differential form. And so as I said earlier, the term local here corresponds to the fact that it depends on the formal neighborhood of a point. So that's the notion of a Lagrangian in these terms. And now we can see that the earlier Lagrange equations are obtained in the following way. So we take the horizontal forms, which are just the set of morphisms from E to E plus 1 external power of the cotangent bundle. They're called horizontal because these are not all forms on E. It would be just morphisms into the universal sheaf of differential forms. No, these are just forms which are sort of induced from the manifold below. So these are horizontal forms on E.
So we fix some connection, yes?
Yes, in a sense, yes. Yes, I do not specify it explicitly, but I think you can do it that way as well. Yes. And so, since L is an element of these horizontal forms, which are a subspace of all t+1 forms on this jet bundle. The differential of L is not necessarily a horizontal form. So we can apply the differential, the Durham differential, to this differential form L, and we obtain the following. So we obtain a certain form which is which has degree t+1 horizontally and degree 1 vertically. So jet bundle acquires a bigradient on its complex of differential forms, on its Durham complex, where 1 degree is given by the degree on the base, and another degree is given by the degree on the fiber. So this EL form is a form which has degree 1 on the fiber. And also we have a horizontal differential of some horizontal form. So this Euler-Lagrange form, it absorbs all the contributions which we obtain vertically. And it is a source form, but I will explain what source forms are later. So Euler-Lagrange equations of a field theory actually are obtained in the following way. So if we have a section which is a configuration from sigma to E, then what we should do is the following. So assume that we have an arbitrary vector field on this jet bundle, then the Euler-Lagrange equations state the following. So we should contract the Euler-Lagrange form with this vector field, and then we should pull the obtained differential form back using the infinite extension of our section. And then we should get 0. So that's the general way of formulating Euler-Lagrange equations for a field theory. Okay. So now let's recall some general categorical background. So what is an Erlenberg-Moore category, in this case of a monad, but obviously the same construction applies for comonads. Another name for it is, of course, a category of algebras over a monad or co-algebras over a comonad. So assume that we have a monad, then a T algebra is just an object in the category C, together with a map from TA to A, such that the composition of this map with the multiplication of this monad restricted to A coincides with this composition. And another condition is that if we compose it with the unit of the monad, we obtain the identity map on this object. So the multiplication is the map like this, and the unit is the map like this. So that's just the Erlenberg-Moore category of a monad. It's very, very standard. But what we get here? Well, actually, if we take the Erlenberg-Moore category of the jet bundle comonad, we obtain the category of partial differential equations on a manifold. So the objects of this category are partial differential equations on sections of bundles, so various bundles. We don't fix one bundle, we consider all bundles. And morphisms are, differential operators which preserve solutions of these partial differential equations. And it is a result of Marwan from 1989 that states that this category of partial differential equations is actually equivalent to the Ehrenberg-Moore category of the jet bundle comonad. So a bit of context, Marwan was a mathematician working with Vinogradov, if you know, I don't know, Jet Nestruyev's book or book about homological aspects of partial differential equations. That's Vinogradov's school. So yeah, he was working on the Faculty of Mechanics and Mathematics in Moscow. Yeah, and this thesis of his is actually written in Russian, which is quite funny because somehow NLab references a thesis written in Russian, and I don't know what they expect people to do. But the result, nevertheless, is this beautiful equivalence between purely categorical construction of a jet bundle comonad and very concrete, in a sense, category of partial differential equations. So we can think of partial differential equations categorically.
Could you recall what is a differential operator in this context?
Well, I think I don't want to do it right now, but yes. Well, there is of course a stupid coordinate way to do that. So you can do you can like say that it is represented by some sums of some composites of derivatives with respect to local variables, and in a sense it's sufficient for our purposes. So just think of something that can be written as a sum of compositions of partial derivations. That's the definition that you can use, because we will not use any properties of differential operators here. And I guess that's enough. So that's just
and
yeah.
it looks like a connection operator. So it sends sections to sections, or
yes, of course, yeah. Of course, it's okay. It's an operator. Yes, that's very important. Yes, that's very important. That yes, of course, it's an operator on sections, and locally it can be written as sum of some compositions of partial derivations. Yes, thank you for this clarification. Yes. Okay. Okay, so assume that let's discuss source forms a bit, since they already appeared as the place where our earlier Lagrange form lives. So assume that we have a smooth bundle. Then we can take the Durham complex of this jet bundle, since we've already seen that we can take Durham complex of any sheaf. It shouldn't scare us, even though the jet bundle is infinite dimensional. It doesn't matter. We still can take the Durham complex of it. And this Durham complex is bigraded. So we have a horizontal gradient, which corresponds to the gradient on sigma. And we have the vertical gradient, which corresponds to the gradient in a fiber. So if we have a differential form of an arbitrary degree horizontally and of degree 1 vertically, then we say that it is a source form if the contraction with any vector field on this jet bundle only depends on the projection of this vector field onto our bundle E below. So doesn't depend on this jet bundle part in an essential way. And as an example, we have this early Lagrange source form. Okay. So now we arrive to a certain picture which describes classical variational local field theories. So first of all, we note that this space of source forms on a bundle becomes representable in the category of sheaves on the category of partial differential equations. I don't want to describe the Grothendieck topology here, but if you want, you can just think of pre-sheaves for a moment. It's not very relevant. And then, since this thing is representable, a classical field theory can be actually described like this. So we have a manifold sigma, we have a section of the bundle E over it, then we have the early Lagrange form, which corresponds to a morphism from E to universal object representing source forms. Then we have the Lagrangian, which is of course a morphism to the universal sheaf of horizontal forms. We have the variational differential, which starts from a horizontal form and increases the second degree by 1, then gives us a source form. And we have an early Lagrange equation, which is the kernel in the category of sheaves of partial differential equations, or even just on a category of partial differential equations of this morphism. So this is actually an object in the category of partial differential equations. Although the kernel is taken in this category, the category of partial differential equations embeds fully faithfully into the category of sheaves by Ioannidis lemma, and thus we obtain the early Lagrange equation as an object of the category of partial differential equations. And then the solution to such an equation is a lift like this. And of course, this diagram can be refined to encompass not only classical variation local field theories, but also classical local variational field theories. This means that instead of considering just map straight from E to this sheaf, we actually consider a certain covering family on E, and then we're considering a morphism not from E, but from the disjoint union of the covering sets. So we don't have the Lagrangian globally, but we have local Lagrangians. And we will discuss this in detail a bit later. So actually right now. Okay, so let's start from a Lagrangian P+1 form. Then we say that an action functional on a section is the following integral. So we take the section, we take its infinite jet extension, we pull back the Lagrangian form to the jet bundle, from the jet bundle to our manifold sigma, and then we integrate it. So that's called the action functional. It corresponds to the classical action functional we have in physics. But what should we do for locally defined forms? So there could be a situation where we only have Lagrangians locally over some covering family of sigma. then we don't have an invariant way to define what is the action function on a section. If we have a family of forms LIs, what is the invariant interpretation of such an integral? Well, here we arrive to the idea of differential cohomology. Well, not precisely differential cohomology, but some considerations which lead to the general concept of differential cohomology. So we start from something which is called Check-Durham cocycles. So the check approach is the following. Of course, we have these differential forms which are defined on the elements of the covering. Then we want to choose differential forms of degree p on the double intersections of the elements of the covering, so that the difference between these local Lagrangians becomes the differential of this p form. So the difference may be not zero, but it is exact. So it doesn't show up in the integral over something of dimension p plus 1. Then we can continue this process. So we take these p forms, we take this.
So sorry. Why this is a exact?
Form. we just want it to be an exact form. We want to find such forms that it is exact. So it's just a construction. I am not saying that it always exists. So then we continue this process. So we want to find a p-1 form which sort of annihilates this cocycle condition. So we take plus minus plus, and we want the resulting form to be exact as well. And then we continue this process up to degree 0. So in the end, we arrive to some functions which live on intersection of p plus 1 sets, and their differentials should be their horizontal differentials should be the corresponding signed sum of previous differential 1 forms. So this collection is called a p plus 2-dimensional Check-Durham cocycle. Okay. So now we can define what is an action functional, but for this Check-Durham cocycle. So it's not a globally defined differential form, but it is a collection of differential forms in each dimension, which approximates a not necessarily globally defined form. And we do it like this. So these are p plus 1 forms. So we integrate them. So we start by doing the following. So we choose a triangulation of our manifold, which is subordinate to our covering. And we do the following. So we start from p plus 1 forms, and we integrate them over p plus 1 simplices of this triangulation. Then we take p simplices, and we integrate p forms, and so on. And so the resulting integral becomes invariant. In what sense? Well, it becomes invariant.
Sorry, why we have a triangulation here?
Well, we're living on a manifold. I mean, we live on sigma. And as we know, any smooth manifold can be triangulated, although never asked me to prove this.
Okay.
And I guess we even have the statement that if we have I don't know, a locally finite covering of this manifold by open subsets, then we have a subordinate triangulation. So yeah, we use this this fact. So why this definition, which integrates the whole cocycle over different dimensions, is good? Why it is invariant, and in what sense? So it is invariant under something that's called gauge transformations. So what is a gauge transformation? So a gauge transformation is something that is also given by a P+1 chain. So we also have this collection of forms, and a gauge transformation of Chuck-Durand cocycle is the following. So to P+1 forms, we add horizontal differentials of P forms. Then to P forms, we add horizontal differential of P-1 form from this collection, corresponding to an element of a covering, and a difference between P forms, which corresponds to this segment ij, and so on. So, in a sense, yeah, in a sense, it's like a multiplication. This group of chains, but the idea is that our integral should be invariant under such transformations. So I guess in physics, an operation like this would correspond to some kind of renormalization of our system, and we should still get something invariant after such an operation. But it turns out that forcing an invariance under gauge transformations creates some problems for our approach. And the thing is that if our action functional is invariant under gauge transformations and it is valued in real numbers, then actually there is no non-trivial Chuck-Durand cocycles. So any cocycle is equivalent under gauge transformations to a cocycle which corresponds to a globally defined P+1 form. So obviously, if we have a P+1 form, then we can define a Chuck-Durand cocycle which just does not have any kappas of any degree. So they are all zero, because for a globally defined form, obviously all these differences are zero. And so if a system has an R-valued action functional, it actually means that the system is given by a globally defined differential form. But as it turns out, not all physical systems can be given by globally defined differential forms. And so a fix to this, suggested by Dirac, I guess, is to consider not R-valued forms, but forms which are valued, for example, in a circle group. So we can consider this as the place where we consider our smooth functions. So now we say that kappa zeros with some index are functions with values in the circle group. This, however, creates problems of its own, namely that our action functional is no longer has a unique value, it only has a unique real value up to gamma. where gamma is this discrete subgroup of real numbers. But
sorry, could you repeat what is the problem at this point?
Oh, the problem is the following. So if we have real valued functional or real valued kappas, then the condition that the functional is invariant under gauge transformations forces our system to be globally defined, meaning that all these LIs are actually equivalent to some, LIs are actually equivalent to some L hat I, such that L hat I is just the restriction of some globally defined form to UI. However, there exists physical theories which do not arise this way. So there is no way to define a global form which describes their behavior. There's only some local descriptions.
Okay.
Yeah, so the problem is like this, and a fix is to consider a circle valued functions instead of real valued ones. And as it turns out, we can actually classify all Chap-Durand cocycles in a category of sheaves on partial differential equations valued in chain complexes. So so if we have a horizontal form on our manifold, we can pass to this Chap-Durand cocycle, which corresponds to our form in the way I described earlier. So we just take all kappas to be equal to 0. And this is actually sort of a covering map in an appropriate sense. So I guess in terms of our previous talk, it is a generalized cover. And this sheaf, which classifies Chap-Durand cocycles, lives in the category of sheaves on the category of partial differential equations over our manifold valued in chain complexes. And then using the Dalt-Kahn correspondence, we can obtain sheaves of partial differential equations valued in simplicial sets, which means that, well, this category corresponds to higher topos of sheaves on this category. And actually, we can explicitly describe how this sheaf works. So this sheaf already has a name. It's called Deligne complex, or in this case, a universal Deligne complex. So we take the following complex. We take integers, we embed them into horizontal zero forms, like this. So we map each integer into a locally constant function with value 2ph times n, where n is this integer. And then we apply the horizontal differential to obtain this complex of horizontal forms. So this is called horizontal Deligne complex. And this means that Chap-Deligne cocycles correspond to cocycles in, well, this set of maps from sigma to this sheaf. And as I said earlier, we actually have a covering map from our P+1 horizontal forms. So it's readable here, but we have a covering map from P+1 forms into these into this horizontal dealing complex. Okay. So now we can say something about prequantization of the earlier Lagrange form. So we can describe what is a prequantization of the earlier Lagrange form. So first of all, we have this variational differential, which maps p+1 forms into p+1 source forms, which are additionally closed because it's an immature differential. Then we have this covering map from forms to horizontal dealing complex. And then we have a map which is called curvature from the horizontal dealing complex into source forms. Okay. Then what is the prequantization of the early Lagrange form? Well, actually, it's just a lift of the early Lagrange form along the curvature map. And so that's an appropriate way to sort of generalize or, well, frequentize the early Lagrange form. And this gives us the general picture for local field theories. So it is similar to the picture we saw earlier. So we start from our spacetime, we get a configuration. Then we have some covering of our field bundle. Then we have the locally defined Lagrangians, which are valued in. So these are maps from the elements of this covering family to horizontal forms of degree p+1. Then we have so we have this covering map here from horizontal forms to horizontal dealing complex. Then we have the curvature map, and we have the variational differential. So this prequantized early Lagrange form fits into this picture here, and this composite should be the early Lagrange form itself. And this basically describes the prequantization of early Lagrange form for locally Lagrangian field theory. Yeah. So let me remind you what was the purpose of all this prequantization business. So as we saw earlier, there is a need for some interpolation between quantum systems and classical systems. And that's precisely it. So if we consider a classical system, it is given just by the usual early Lagrange form. But if we want to prequantize it, we need to lift it to some higher object, which is defined only in the infinity sheaves on our category of partial differential equations. And that's precisely what we do. So on the one hand, we can obtain the usual system by taking curvature of this prequantization of early Lagrange form. And on the other hand, we can obtain the quantum version of all this by taking the geometric quantization, which I unfortunately did not have time today to explain, but that's another side of this story, which produces the fully fledged quantum system from our pre-quantum construction. So I guess this is it for today, and hopefully to be continued. And hopefully I will be able to explain how geometric quantization works, at least in very broad strokes, and how it is related to all this business about higher categories. Okay, so if there are any questions, please ask them. I will stop the recording.